module 46 on feature scaling and regularization, which in some sense are two separate topics, but they come together in interesting ways. Hopefully today will be interesting for you. So by the end of this module, you ought to be able to explain in plain language, the language of your choice, I guess, how scaling affects distance-based models and regularized linear models. We're going to define what regularized means today. You ought to be able to choose and justify a scaling strategy, although we've talked about that in previous modules. But you're going to apply it within the context of machine learning now. You ought to be able to implement ridge and lasso regression. We're going to define these in a moment using scikit-learn, our dependable Python library, within cross-validation, which we've talked about, and we'll use that to pick a regularization strength. You ought to be able also to diagnose from plots and metrics when missing scaling or mistuned regularization is likely to be the main problem. So we already know that we want to put our input features on comparable numeric scales so that when we optimize, we're going to optimize nicely. Back in the past, when I talked about the vast differences between the units that we sometimes obtain in our data sets, I kind of hinted at the fact that this is potentially going to be a challenge when we want to fit a model to the data, and some variables just have very big scales, like their units are in very big numbers, and other ones are smaller. And when we're going to be doing machine learning models that are based on optimization, it'll be increasingly hard to do that when you have this kind of disparity. Similarly, if you want to measure the distances between two data points, which a lot of the time, increasingly in the machine learning context, can be conceptualized as numerical vectors in space. How do you actually measure the distance between them? It's like a straight line distance. But if one of the axes along which you're measuring straight line distances is just stretched a lot more and much greater magnitude, then that's going to have a huge influence on what you consider to be distance. And what we want is this concept called regularization, which will penalize features in a fair way that will still help you do optimization at all. So the key idea is, again, going back to what we talked about in previous modules, the features units, like this, the mere fact that we're measuring one variable in years and another one in dollars, another one maybe in GPA, that the mere fact that these units exist shouldn't by themselves influence like the model in undue ways. And how do the units affect models in undue ways? Well, we've already seen a couple of methods, in particular k-nearest neighbors, as a form of doing classification that is explicitly based on distance. Like, how do you measure which neighbors are near or not near? A little bit later on, we're going to see another algorithm called k-means, which is used for clustering that also requires distance. So actually, we're going to introduce ridge and lasso. We're not going to really see elastic net. I'm probably not going to mention it again. And in case I don't remember to mention it again, elastic net is just a weighted combination of what we're going to see called ridge and what we're going to see called lasso. These are two just different algorithms, and their weighted combination is called elastic net. So when you're doing some kind of gradient-based method, we talked about gradient-based methods, like where you take steps towards an optimization. We talked about that in the context of OLS. You kind of assume that these gradients, as you're moving down into these loss or risk curvatures, that the distances in the different directions are more or less kind of uniformly on the same scale. We've already seen how to do scaling. We've even seen standard scaler being used from scikit-learn's preprocessing sublibrary. So we don't really have to get into it again here, but here's the implementation of it. We just create a standard scalar object, call it scalar, and then we fit the data that we have using that scalar, and then we can plot before and after. And xraw, in this case, is just randomly sampled data with some noise. So nothing too fancy here. We have two features. It's called A and B. The overall shape of the data, as you can obviously see, is exactly the same. It's just that we've applied z-score normalization to ensure that in each of these two directions, what we call feature A and feature B, the mean will be 0 in each of those dimensions, and then the standard deviation in each of those dimensions will be 1. Okay, so unscaled on the left, scaled on the right, but the overall distribution of the data is fundamentally unchanged. So if I'm jumping right into it. We talked a little bit about the effects of complexity in models. And when you have models that are very flexible, by that I mean you have lots of parameters you can adjust through learning. They're highly capacious, they have a high capacity, which means that they can learn a lot of different things because of all this flexibility that they have. And then you also have data, on the other hand, that's noisy. All data ought to be noisy to some extent from the real world. Some of this noise is induced from sensors, including anything, including even text itself. Some of it is induced by the nature of the process that's generating the data. We talked about that earlier also. But if you have a very powerful model, or flexible, as I call it here, and you have noisy data, then the model can learn the patterns in the noise, and it can be so flexible that it can maximize its performance on recognizing the pattern in the original training data. And I may not have emphasized this enough in the past, but one of the main purposes of doing machine learning is to not just learn a model and then look at it and how beautiful it is. We want to deploy it, and we want to run it on future unseen examples in the real world. Every use of AI that we see in the real world is used on new prompts that have never been written before, new speech requests that have never been uttered before, and so on. So we want to make sure that our models generalize to things they never saw before. And what that means is that if they're just super performant or super good on the training data, so good in fact that they are unable to recognize any situation or condition outside of the world of the training data, then that's overfitting. It's too good at the training data, and that's something we want to avoid. So the good old-fashioned OLS, which we talked about in a previous module, will pick our parameters, which are sometimes called theta. In my machine learning class, I call this theta. In some situations, we call this W for weight. Here, we're calling it beta, just for the convention of practical data science. And beta hat means like the best possible setting given the data that we have. When I say best possible setting, I mean, given the training data, we want to minimize the squared error in making predictions on the training data. And choosing the parameters of the model, beta hat, minimizes that error. Now, if there are many features, and some of these features are redundant, or some of these features are highly correlated, I put this in sort of the logical form. If it's this, or this, or this, or any combination of them, then we can end up fitting the noise, like I mentioned, not the signal. That's a bit of a different problem than overfitting, but they're closely related, so I'm going to leave it there for now. The nuance is not important. Normally what happens when you train a model like this is that the parameters get very big. We're going to see some examples of that later today. So when you're trying to choose these beta hats, the beta hats that are the best for the training data end up being very large in situations when you're overfitting just to the training data, and therefore not doing very well in new tasks and generalization. So what we want is we want to take what I'm calling a loss function now. This is really, to be proper, it should be called a risk function. We saw this last time. It's sort of the average squared difference between our predictions, y hat, and what we know to be, quote, true, y. So this is just the difference squared, and then we take the average in the familiar form of average. This is called a mean squared error loss function, or it's the empirical risk function technically, but we're calling it loss now because so many other people call it loss. But we add this other term. So we're not going to just try to make our predictions as close to the truth as possible, like we're doing on this left term. We're also going to have another term we want to make as small as possible. We're going to want to make our individual parameters beta also as small as possible. Okay, we don't want our parameters to be too big because otherwise our predictions are going to fluctuate crazily. So when you're finding values of beta that are going to be optimum, they're going to be the best values of beta we can find. Make the most accurate predictions you can, but also do so by making your coefficients as small as possible so that the curves are smooth. In this case, we have like p parameters that we can adjust, which is this p up here. And we also have this new factor lambda. Lambda is just a number that we can tune ourselves. In fact, I'll talk about it in a few moments. This is sort of a weight. Okay, so how much of our overall goodness function or anti-goodness function, this loss, do we want to assign to just making good predictions, MSE, and how much do we want to assign to making sure the prediction function is smooth and not too chaotic by making their parameters small. So that's the ridge regression, where we're taking, like this blue part is this ridge regression, we call L2. And then lasso regression, or L1, is the exact same thing. So we still have the original mean squared error term here on the left. We still add lambda times something. That something is still a sum over all of our parameters. But instead of taking the square of our parameters, we just take the absolute value of our parameters. Same kind of idea, and we want to make this as small as possible. So make the absolute value of our parameters as small as possible, also while you're minimizing the average sum of squared errors. So a few things here. So this form should be pretty easy to remember. Like, you can write it down a few times on paper. That sometimes works for me. But I mean, conceptually, it's pretty straightforward, right? We're just literally just summing over all of our parameters, the things we can adjust, and then we're weighting those parameters by some amount lambda. You're going to hear people say ridge this and lasso that, or L2 this and L1 that. And you know, luckily, machine learning has a lot of mnemonics that we can use to remember what these things are. And the one that works for me, even to this day, to be honest, is if you look at these regularization terms we're adding, the first one I mentioned squares every parameter, and the second one is sort of linear. It just takes the absolute value. So we'd call this order 2 in the first case and order 1 in the last case. And then if you recognize that, then you'll very easily recognize that, well, L2 refers to the second order case, so these 2's, and then the L1 refers to the first order case. Okay, so that's an easy way of mapping L2 to where we're squaring their weights, and L1 to when we're taking the absolute values. How do you remember which is called lasso and which is called ridge? This is another little hack that I'm not ashamed to say still works for me also. You just mention these things alphabetically. L1 comes before L2 alphabetically. Lasso comes before ridge alphabetically. And you're done. So now you remember lasso is before ridge, L1 is before ridge, therefore lasso is before ridge, L1 is before L2, therefore lasso is L1 and ridge is L2. I think that's basically it. You're going to still have to do a little bit of learning. You're going to have to remember that we're calling these L1 and L2 as opposed to some other letter, and you're also going to have to remember that the words are lasso and ridge. These always sounded a bit like, that's the terminology of someone who lives out in Alberta, that they would use for wrangling their livestock. But there you have it. So lasso and ridge. So I mentioned I was going to talk a little bit about lambda. So lambda is like a knob. Sometimes this is called a happy sad knob, although like the ends aren't really happy or sad. They're not good or bad. They're just the amount to which you want to give priority to these new regularization terms. If lambda is 0, then obviously this, in both cases, the whole second term disappears and we're left with our good old-fashioned mean squared error. The more you increase lambda, the more you end up with with like the betas being smaller. Therefore, your model is going to be kind of simpler or smoother, and this is going to result in what we call more bias but less variance. So you're going to kind of make the same kind of prediction typically on average, but the variance will be less crazy. Like, you're going to make less crazy predictions. Again, if this doesn't make sense right now, we're going to see an example of this in the worked example section. Two interesting phenomena, which I like. L2 tends to kind of shrink the coefficients smoothly. And I can't remember if I showed you an example in this class. I'm getting my wires crossed because we also talked about this in my third year machine learning class a little bit. If you want, I can send you the links to that slide deck where you can see a lot more detail about what I'm talking about, which won't be necessary for this class, just FYI. So L2 tends to shrink the coefficients, so you still have like betas from beta sub 1 to beta sub p, but they're just kind of smoothly shrunk. L1 tends to actually set a bunch of the features to 0 exactly, which is an interesting phenomenon here. We're not going to talk too much more about that, except to say that, well, if lasso regression, just by using it for training, kind of naturally ends up setting some of these beta values to 0, in some sense that's an indication that the overall training process has learned that those weights are not important to making prediction. So they're unimportant, they can be zeroed out. Again, I mentioned before, maybe 2 of your features are highly correlated with one another. So if you know one, you know the other. And when you're making predictions in this sort of model, you'll have a beta value multiplied by 1 and another beta value multiplied by the other. If they're both correlated with one another, you don't need both of those variables. So you can set one of those betas to 0 and basically turn off that feature and only use the other one. This can be helpful for explaining what the model is learning, like, oh, these features are important for this task, those features are not important for this task, which is a bit crude, but it can work in some situations. And it also can help you with engineering. So if you find that 80% of your features have ended up through regularization with L1, have ended up with 0 values for their respective betas, then you don't need to do all the work of computing them and storing them and doing all that work. So you can kind of trim things down and still have a highly performant system. This is just a little graph. It's very highly theoretical. It just basically shows kind of the idea of what's happening. Here we have like the loss function, and you have values of beta, and you have what we talked about before, the mean squared error, which is this blue curve. You can get loss to be pretty low. In fact, you can get the overall loss to be lower than if you have the penalty. And if you have the penalty indicated by this orange curve, so you're training both minimizing the mean squared error loss, and you're also trying to make your parameters beta a bit smooth, you tend to move the parameters over a bit, so the values you're going to end up getting as optimum are going to be a little bit different, and the loss function you're going to get is going to have a kind of higher minimum, so it's going to end up looking a little bit worse on your training data. And but the net result of that is still going to work out. It's going to mean that we're going to have a system that deploys a lot more effectively, and that's basically one of the main purposes of this class. It's called practical data science. We're not just doing data science for its own sake. We want the models to be deployed. So therefore, when we're looking at performance on training data versus performance on test data, or validation data, the latter is preeminently important. So just a little example of this idea we talked about before, about units deciding who gets penalized. So suppose you have a lasso model with no scaling. So we potentially have a lasso model. We have a lasso model. We're using L1, and we're not scaling our features. So we're just using raw age in years and raw income in dollars. And we do have the lasso L1 penalty, so we have this little term that we talked about previously. If you change, so you're going to have weights for each of these variables, obviously, right? We talked about that, like feature A has beta sub A attached to it. Feature B has beta sub B attached to it. So there's a weighting for age or income here, and there's a beta for age. If you have the situation, a small change or any change in the beta of income can change the predictions you make much more than the same absolute change in beta of age. So if you increase the weight of income, beta sub income, by 0.1, that's going to have a much bigger effect because you're multiplying that by inputs that are on the order of hundreds of thousands. Whereas an increase of 0.1 in age, that weight is only on a range of like a few dozen units. So overall predictions will suddenly fluctuate a lot more, right? So then therefore the importance of these different betas is not uniform like we kind of expect, but there's an inherent difference in how important these different values of beta are. And therefore the optimizer, which again is just going to steadfastly try to optimize for the weighted combination of mean squared error and its L1 penalty. It will shrink coefficients for the large-scale features very aggressively, and it will either keep or drop features in ways that will reflect the units. So like I mentioned before, it'll maybe set betas to 0 in a way that's just mostly focused on the scale of the units and not so much on the value of the features' actual measurements. So it won't actually become predictive. It'll be sort of a unit measurement predictor, right? So it'll recognize, okay, like just give a big weight to whatever is in this this variable because its scale is so much bigger, and it's not going to care anything about the distribution of the values in that variable, nor its relation to whatever it's trying to predict. I'm speaking a bit kind of loosely here, but that's sort of the fundamental idea. So when we're doing L1 and we're kind of selecting features by setting some of their betas to 0, everything will be very arbitrary. It'll be based on something that's not very data dependent, which is what we want. It'll be based on something else, which is no good. So the solution to this, amongst some others, is to scale the features first. So like when we talked about standardization and min-max scaling earlier, it wasn't just for fun. Like this was most of the reason why we were doing scaling in previous modules. So whenever you're going to do L1 or L2 penalties, or indeed any kind of training, it's going to be a good idea to standardize first with z-scores and scalars like we had a few moments ago in code. So this is under the microscope, so don't worry about it too much. We talked about OLS before, and we want to talk about ridge regression as being sort of a softly constrained OLS. This is going to require lean on some linear algebra a little bit, so this can rightly be called an aside, because this is a bit outside of the scope of this class, or what's important in this class, but it's still, fundamentally important for you to understand these concepts, so here it is. So we had the OLS solution we talked about in a previous module. Like the best value of beta is going to be the input matrix X transposed times X, all inverted, times X transposed times Y. And this is going to give us analytically our best possible values of beta, as long as X transpose X is invertible. So that's a whole other topic, which we can take as read for now. For ridge regression, remember R comes after L, therefore this is L2 regression. We want to minimize this so-called loss function. So it's basically the norm of our MSE. So this is just a fancier, somewhat fancier, more like matrix-oriented way of showing the average of the sum of squared differences. This is the same formula. You can go all the way back to the beginning of this course where we defined norms. But X times beta is just a prediction, right? This is literally the linear predictions that we're making, which we called Y hat a moment ago, and we just compare them against Y, what we should be predicting if we were accurate, perfectly accurate. And then we have the two norm of our beta values. This is just the L2 ridge regression, ridge regularization penalty multiplied by lambda. So we can solve this new ridge regression here. So now we have our old MSE term and our new ridge regression regularization term. And following basically the steps that we talked about in a previous module, again, this is just for the people who can follow along right now. But if you can, it's good to know this stuff and to refresh your memory. I think in a previous module I actually suggested that it's a good idea to know why we're setting derivatives to 0, so maybe that point shouldn't be lost on you. But the kind of deep, derivations or calculus here is not going to be crucially important practically in the class. If you expand each of these norms into their component parts, you can take the derivative of each of these terms separately, because it's just there's an addition here with respect to beta. So take the second term here, the ridge regression term. This entire thing will just be to take down the 2 from the polynomial, and there it is, multiplied by lambda times whatever was in the function u according to the chain rule, which is just beta, which are vector of all of our parameters. And then we take the derivative of, and then we're done. It is just like we're finished this term. Next, we take the derivative of this function over here, this term over here. So again, this is a polynomial of a function of the variable we care about. We take down the 2 from the polynomial. There it is, multiplied by the function itself, which is in here, which is just y minus our prediction, x times beta. I kind of shuffled around the factors of this term a little bit. And then you take the derivative of this function with regards to beta. This is because there's an invisible beta to the power of 0 over here, so this inner term here with y goes to 0. Here, this is minus x beta, and this is still a polynomial of degree 1. So the derivative of this with regards to beta is just minus x and then here it is. And it's transposed, so we can multiply these things together. And then we take this derivative and set it to 0. And because this is quadratic, we know that when this function gets to its minimum, that's when the curve will have a derivative of 0. So whatever that point is, where the derivative of 0, that's the point where we have our optimum setting of beta. So we're going to solve for beta. Next, we can just multiply things out, like multiply minus 2x transpose into this little bit. And then we shuffle things around. We end up with, well, first of all, we can divide everything by 2, because now there'll be unnecessary 2's on every term. So we divide by 2, we move minus x transpose y over to the other side, and then we group together the betas, and then we divide by x transpose times x plus lambda I. I is the identity matrix. It's like a 1 in normal arithmetic, and it's there just so we can do these steps. So here's the so-called division. I'm speaking a bit loose here. I'm trying to go fast again because this is kind of super interesting, but not practically necessary for things like the modules and the notebooks. So anyways, there we are. So this is the solution for finding the optimal values of beta, our parameters, under the condition that we're doing ridge regression, that is to say, a mean squared error with the L2 regularization. So how does it compare? Well, we can kind of look at the good old OLS solution, which is the solution we got for our values of beta when we were not using regularization. We can compare the beta set sub OLS to beta hat sub ridge. And the only difference here really is that we kind of add this factor plus lambda I within this term that we're dividing everything by. So in some sense, we're nudging this matrix x transpose x towards something that is better conditioned for our problem by just adding these lambdas. So when our predictors are going to be highly correlated, so when the input variables in x are highly correlated with one another, this product can become very nearly singular, and which is a problem, but ridge regression basically stabilizes this inversion. So again, just like we talked about before, when lambda is close to 0, when we're not doing much regularization, then this term disappears and we're left with our solution to that we got previously with OLS. So we've gained nothing if we set lambda equal to 0. If you increase lambda to infinity, then basically beta sub ridge goes to 0. This is a really pathological case. You'd never really do this in practice. We're not going to derive the full lasso closed form here. It's a bit more complicated because of the absolute values. But there are optimization routines in sklearn that kind of do the work for you anyway. So it's very good to know the theory always, but you'll always have the practical tools, surface level, for each of these kinds of optimizations. I'll keep on going for now. These are some examples. So the first example is we're going to look at scaling and ridge coefficients. We're going to predict a continuous target. We're going to do a regression. We're going to have 2 features only, but those features are going to be in very different units. We're going to generate some synthetic data with coefficients that we know. We're going to fit a ridge model without scaling, and we're going to fit a ridge model with standardization in our pipeline. And then we're going to compare the learned coefficients, and we'll discuss what they mean. Again, it's always good to have an understanding of what the model is doing. It's inappropriate just to put numbers into a table and then ship it. We need to have some kind of understanding of what's going on. So nothing much more is happening here. We're going to have an age variable with average is 50. Its standard deviation is 5. There's going to be n examples here, sampled from the normal distribution. We're going to produce income. The average is going to be $100,000, and it's going to scale at the standard deviation is 15,000. It's also sampled from a normal distribution. This will just be put together in one big stack of our inputs x. We have true coefficients here, so this is going to be 0.7 times one and 0.00003 times the other. We're going to have a little bit of noise just to, and to some extent replicate the real world. And then we're going to have the true values that we want to predict is going to be our inputs times what the true values of beta should be, plus this like real world noise. Okay, we've talked about this at operator in previous modules also. This just allows us to do matrix and vector multiplication easily in Python. We have ridge, which is a linear model. This is just like linear regression with the ridge regularization term added to it. So we have ridge. Here, alpha is what I called lambda before. This is another kind of pet peeve in machine learning. There's so few Greek letters that you end up seeing the same Greek letter serve a lot of different purposes in different contexts. But also sometimes even within the same context, the values change a little bit. You have to use alpha here because alpha is what sklearn calls lambda, or the kind of weighting term for the regularizer, but we're using lambda elsewhere because lambda is what we tend to see it in theory. Anyway, so we create the ridge regression object, and then we can just call our trusty fit function given x and given the true values of y, and we're done. So that's our kind of unscaled version. Next we have the scaled version. We're going to use pipeline because we're trying to be good machine learning engineers and keep things clean. Our pipeline will just have a scalar followed by the ridge regression. Again, changing as little as possible, so we're going to use the same values of alpha, the weight, which we called lambda a moment ago, and then once again, just do our fitting. And then we'll just put everything into a data frame so we can look at it in a pretty fashion and print it out to our slides. And here we can see a huge difference, right? So here's our two features. When we're not using scaling, when we haven't done the Z scaling of our features, we have like several orders of magnitude bigger features on age than on income. And when we actually scale the features before doing the fitting, then we're still an order of magnitude difference. Like the beta in the scaled case is 3.3 compared to 0.5-ish for income. But this difference is a lot less stark than the other, right? So this sort of exemplifies a little bit of what I was talking about before. When you're not doing scaling and you're fitting a model just kind of blindly with whatever data you're given, even with ridge regression, like ridge regression is supposed to be the form of regularization that does not ignore features entirely. That was supposed to be lasso, the first order one with absolute values. Multiplying by 0.00003 is going to be basically ignoring this feature. Here's just a visualization of what we saw before. So without scaling, the raw income coefficient will be tiny in magnitude compared to the age coefficient, but that doesn't let us interpret that income is actually unimportant. It's just that its values are way bigger. So you have to multiply by very tiny values of beta in order to get them to be comparable. With scaling, the coefficients, so here you can see like the income betas are basically, they've disappeared in this graph. When you've done scaling, the coefficients are going to be themselves kind of standardized. So we can compare beta in one feature and beta in the other, and that will tell us something about how important the data in those features actually are, the actual distributions are, as opposed to just the units. So we're not just learning units now, we're learning something about the data itself, which is the goal. So any kind of differences here, like the difference between income and age, now we can say, yeah, like it's not just a weird factor of the units that is making income seem so unimportant. Income is less important than age, but not to the extent that we would imagine it without scaling. We set a particular value of lambda, we call that alpha because sklearn calls it alpha, and this can have an effect. So as always, I'd advise you to take the code I'm giving you and put it into a Jupyter notebook and just fiddle with it and try to break it. Change alpha to 0.1, change it to 100, and just do the experiments and see what happens. And that's all I'm going to say about that for now. Here's another example. We want to tame overfitting. So remember, overfitting was the situation where learning on training data you had such a powerful model that you could become like arbitrarily good at performing on the training data, but you're no good in the real world. There's lots of corollaries for this. You can imagine somebody who does really well in an exam in a class, but then they fail to apply their skills in the real world. And it's obviously none of you. All of you are going to do great in both of those ventures, but the same kind of metaphor applies. So we're going to try to fit a smooth curve. We're going to do regression. So we're going to fit a smooth curve that's going to try to fit a flexible polynomial. So that means we're going to have a function that's going to have lots of features. It's going to be very powerful, or relatively very powerful, or very capacious, or very flexible model. And then after that, we're going to use the ridge regularization term, the L2 term, to minimize the effect of this overfitting, so that we can make sure that our model is still going to generalize well and we can deploy it in the real world. So our true function is just going to be the simple sinusoid, a sine of 2 pi x, where x is our inputs, and we're going to have some real world noise. And x is going to go on the range of 0 to 1, and that's it. So polynomials, often you'll see them, they have a degree 3, which means you have like x cubed times something plus x squared times something plus x times something plus something will be your prediction. Here we have degree 15, so like x to the 15 times something plus, blah, 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 you get the idea. We'll have all these parameters, the somethings I'm talking about, those are the betas, the weights, and we're going to find the values of beta that are optimum with no regularization, like using the methods we talked about previously. Then with the ridge term added with a small lambda, so we're going to regularize but not too much, and then we're going to look at ridge with a larger lambda, so that's regularizing with to a larger extent. So here's the code. Between lines 14 and 16, this is where I'm defining like the truth. I've derived my inputs x. I've defined my noise. I've defined the true values I'm trying to predict. Again, this should not be something I have to say, but just because I haven't mentioned it in a while, these values would not normally be given to you. Like, you don't know the real model in the world that's producing the values y. You're just given y by itself. Like, the fact that we have this line 16 here is just because I'm making this example for you. So we have all these x's and y's now. We need to split it into a train set and a test set. So 70% of this will be for training, 30% of it will be for testing. This function, make poly model, will basically take like a base model and will return a pipeline. So it'll be have polynomial features of degree 15. This, should also be passed as an argument, come to think of it, but it's fine for now. But it's the degree 15 polynomial. There's no bias, so you're not going to have a parameter that's not multiplied by some piece of input. There's a scalar, because we realized just a moment ago in the first example how important scaling is, so we're always going to do scaling. And then it's the base model. So our models are going to be linear regression, ridge with alpha set to 0.1, or lambda set to 0.1, and ridge regression with alpha or lambda set to 10. And then basically for each of our types of model, we will get our pipeline from the function defined starting on line 22. We'll fit it because all of these functions, thanks to sklearn, just have one overloaded function fit, which not overloaded. All these objects all implement the same function fit, given the training inputs, given the training outputs. And then we'll make our predictions, in this case, both on X train and Y, and X validation, or validation set. And we will report on how well we do on the training and on validation. I think I mentioned previously that usually when you report on a machine learning process, we don't often care about training. Like, what matters is the deployment, so we report on validation or validation and test, which again are kind of separate ideas here. But it can still be helpful to look at the training just to see if anything weird's going on. Like if you're unsure about whether you're overfitting or not, or if you're learning anything, then comparing the training values and the testing values can tell you if anything kind of weird is going on. If the training predictions or the training RMSE is very high, you're very bad, then you're not really learning anything. You might have to go back to the drawing board and come up with maybe different hyperparameters, a different whole model architecture. If the training RMSE is very good, that is to say it's very low, and the validation RMSE is very high, that means very bad, that would be an example of overfitting, right? So that's an example where you're doing really, really good on the training data, but whatever you've learned fails to generalize outside of that very specific scenario. So here we have our the results of our little experiment. We have our train RMSEs all the way down. And you can see that when you're not doing any kind of regularization, when we're not using ridge or L2, then that's when you actually get the best possible RMSE values. And remember we saw those two curves, the blue curve and the orange curve? I mentioned that, well, it nudges the betas over a little bit. So the best values you can get for loss will actually be a bit worse on the training data than if you did not have any ridge. But it's going to be worth it, okay? So on training, we do best if we don't do any kind of regularization. But again, I don't care too much about training. Like, what matters is how well we do in practice, in the real world. And if you look at this, well, this is an example of overfitting. Look how much worse our validation RMSE is compared to our training RMSE. We go from 0.265 to 0.441, right? That's a huge increase in root mean squared error. That's pretty bad, right? When ridge is 0.1, so we have a little bit of regularization with the L2 term. We do a little bit worse, about 3 percentage points or so. We do a bit worse on training, but we do kind of consistently well in validation. In fact, kind of accidentally, we actually do a bit better on the validation and deployment on data we've never seen before than we do on the training data. That's great. This seems to be like the ultimate solution. But you know, the alpha values, or what we called lambda before, is a hyperparameter that we can fiddle with. So that's up to us to do experiments with. Here I'm cutting straight to it, like we're doing alpha equals 10, so we're setting alpha to be much, much bigger. So this kind of changes the importance of that two-part term. So we had the mean squared error term, just trying to minimize the sum of squared errors on average, and also trying to minimize the values of our weights beta. But because lambda or alpha is so big, that becomes much more important, and we end up with a model that hasn't really learned anything. Not only is are its predictions very bad, a little bit better than no regularization, but still pretty bad. But also, we really failed to learn anything on this training data. So this is by far the worst training performance we've obtained. Just because like the predictions are less important than making the values of the weights small. So that's why that is. So we have an example of overfitting on row 0, of not learning anything useful on row 2, and you know the third bowl of porridge was just right. Row 1 is ideal. It seems to be ideal. Here's a little visualization of what I mentioned. So these blue training data, that's been generated by that sinusoid, that sine of 2 pi x we talked about earlier. Here's x. X goes from 0 to 1. So each of these curves, the green, orange, and blue curves, are just trying to fit the training data because we're just doing gradient-based optimization like we talked about previously. With no regularization, so the situation we were in before we started this module, we end up with this blue curve, and generally it does a pretty good job, but then it also fluctuates wildly. So the coefficients for the blue curve are going to be bigger. And you can write them out yourself if you want. But that ends up with this kind of highly fluctuating curve, and especially on the right over here, you can see it just explodes up into outer space. So if for some reason you were going to get x being like 1.1 or something, given the true nature of the data, you'd expect to predict something around 0.3, 0.4 or something like that. But our blue curve, which did so well on this training data, would make a prediction of like, I don't know, 1,028 or something like that, 1,024. That would be like obviously a crazy prediction to make on previously unseen data. With the ridge being 10, right? Ridge being 10 means basically squishing down your parameters until they're very small and very smooth. No, the function they define is very smooth. That's this green curve. So this green curve is somehow like lost like any notion of the curvature of the data. It still follows it to some extent, you know, and it still actually jumps up a lot at the end here, but it's underfitting to a large extent. It's not a good representation of the actual changes in the data. It's underfitting. It's not recognizing anything. But the orange curve, where we set alpha to be just right, follows the general shape of our true data pretty well. And we can see that, therefore, it does pretty good on these training data points we see, but also you can imagine other test data being sampled from around these blue dots, and the orange curve will do a reasonably good job of predicting them as well. So unregularized model will have like very low RMSE, and that could mean that it's overfitting. It'll also show wild oscillations like we magically show here. This means like high variance, meaning like its predictions will be all over the place. It'll therefore generalize poorly like we talked about before, and that's not good either. If you increase lambda, if you make regularization too important, the curve definitely becomes smoother and there'll be less variance, there'll be less wiggliness. But the train error will go down, the validation error will also tend to go down, and that's a situation which could be underfitting. And sometimes the coefficients can shrink to zero. I mean, this is really going to be more of a situation when we're doing lasso regularization, that's L1 regularization, which you remember from a few slides ago tends to just turn off some features, but that's as maybe. So looking at the results, you can basically, everything I'm going to mention here is what I just mentioned several times already, so I'm just going to jump ahead a little bit. When you're using regularization, a good mini checklist to use is to always have a baseline. We talked about baselines before a little bit also. I wouldn't recommend using the simplest possible baseline. It's probably not a great idea. So, you know, just predicting the mean is a bad baseline. If you can find another baseline that is not quite so silly and simple, but is simpler than what you're trying to accomplish, that can be a good, floor for your performance. Always comparing to a baseline is like one of the golden rules of being a machine learning engineer. Looking at the training and the validation metrics, not only one or the other, but looking at them both compared to each other and seeing how the dynamics, either they follow each other, or is one way bigger than the other, or are both of them really bad. These are all important symptoms of different kinds of training performance. When you're doing regression, you're trying to predict a value on a constant, a continuous variable. You can use RMSE or mean absolute error as appropriate for the decision context. And then this will, if you're looking for outliers, for example, you can answer questions like, do big errors hurt a lot? Are the penalties all going to be symmetric with one another? So we looked at RMSE mostly in the examples we saw a moment ago, but you can go back to the code and replace RMSE as the evaluation metric with MAE, the mean absolute error. So looking at the residuals, so that's basically just the differences between what you're predicting and what you ought to be predicting. So if there's an obvious curvature, then maybe you need better features, not just stronger regularization. I think we kind of skipped over this in today's module. I took out some stuff for time. I think we're also going to unfortunately have to skip over some of the depth on applying this within the context of k-folds validation. I'll talk about that very briefly at the end. So yeah, in summary, again, the ethical risks we've kind of seen many times already, so I feel like I'm kind of repeating myself a little bit, but it's always good to mention, especially if you're somebody who's kind of cherry picking some slides in this open public course. So these are all technical choices. So choosing the value lambda optimally to optimize like these concave, like quadratic shaped empirical risk functions are technically just technical choices. And whether you do scaling or not, these seem to be just technical, but these technical choices have real world consequences. One of which is you can unequally penalize different subgroups, and in particular different demographic groups. If you're not scaling and there are sensitive features, not necessarily direct sensitive features, but things like region or institution size, like an institution of a school, for example, like an elementary school that may cater to different populations, then regularization might end up like learning those differences that correlate strongly with variables you're not actually observing, and then therefore you might be penalizing one demographic group or the other. We talked a little bit about under-regularization, which ends up overfitting, and we talked about over-regularization, which ends up sometimes in underfitting. If you regularize too much and you make these functions too smooth, then this can sort of wash out or erase effects that might actually matter to unique subgroups or vulnerable subgroups. And if they're already underrepresented, and if we're using regularization to kind of not learn the noise, like the models can sometimes can't know the difference between what is noise and what is just very rare observations from some very small minority group. And if you're just applying regularization sort of across the board, then you can end up sort of erasing the data generated by those small subgroups, and that's a challenge, that's a problem. And then also interpretability. We saw a little bit before, like if you're looking at unscaled coefficients, this can mislead stakeholders. We saw example 1 showed, like if you're looking at the values of beta to tell you how important the different input variables are, but you haven't scaled the input variables themselves, then the scale of those betas will just be dependent on the units of the measurements, and that's not what we really care about. That's not a measure of importance in terms of distribution of data. So, always scale features, and then always apply L1 or L2 penalties. I mentioned ElasticNet before, I'll mention it again. I showed you can either choose L1 or L2. ElasticNet is a third option where that regularization term is going to be some hyperparameter multiplied by the sum of L1 and L2 penalties. And then you have another hyperparameter that tells you how much to weigh L1 versus L2. The first hyperparameter, how much do we do regularization at all? The second hyperparameter, what is the weight between L1 and L2, because we're going to use both. That's called ElasticNet. And again, I can point you to my machine learning class where we talk a little bit about that. Where possible, you should run group-wide diagnostics. So if they're available, you can very quickly look at what performance looks like for different genders, sexes, races, and so on. And ensure that the metrics you're obtaining aren't discriminating against any subgroup. And then documentation. It's not always the most exciting thing for a lot of people, but there are a lot of tools out there that allow you to document machine learning models sort of automatically. Like I talked about MLflow, I think, before, which is a way to kind of just store all of your hyperparameters and your parameters and your models and everything else into neat little containers or packages anyway. So all of the stuff we're talking about is like literally a first-year class. So I'm very proud of you for like following along so far. But like you're seeing like through the cracks towards like the deepest deep learning concepts that you're going to see in years 3 and 4. And we'll talk about weight decay in years 3 and 4 in machine learning, which is there's all kinds of different ways of doing regularization in deep neural networks. But all of them are connected in lots of ways to L2 regularization in lots of different ways. You're going to see sparse models down the line with deep neural networks. You're going to see feature selection, so how to figure out which features are going to be important. And L1 in particular relates to both of these concepts. You want models to maybe not be totally dense. You want to turn off some features or some representations of features. And even if we don't use L1 that often for interpretation in modern explainable AI or interpretable machine learning, the same concepts sort of permeate across the board. When you have, this is off machine learning a little bit, but in signal processing, you also see L1 and L2 penalties, or the respective norms, showing up to recover hidden signals from limited data. To some extent, that is what we're doing with machine learning, but just recovering underlying signals is a task. I might put a reference to some work there also, because signal processing is an interesting thing we don't often see much of in computer science. So, and again, in production, these are all tools that we're talking about that are extremely practical. So scaling, regularization are fairly well encapsulated within these libraries now, and they often are baked into almost every serious machine learning pipeline, tabular or otherwise, actually. And lots of tools that exist, allow you to find the values of lambda that are the best. Like here, we kind of fiddled with it by hand a little bit, just because this is like introduction. But there's lots of ways you can optimize them. I kind of said I'd talk about this in a moment ago. I may talk about it in class, just to not make this video too long. So if you have any questions about how you could find values of lambda that are the best, raise your hand and I'll walk you through it in class, in person. Some questions to keep in mind. How do regularization and scaling interact in classification? So far all we're doing is regression. So we're trying to predict values of y on a scale, but we also have classification. Same general idea, but how do we know how scaling and regularization might affect classification? You might have your own predictions, in which case there should be a little pencil mark over here, and you can think about that and jot it down in your notebook. And yeah, like before you ask me questions in class, how might you find a method to automatically optimize Lambda without having to fiddle it with it by hand? Here are your quick check questions. As always, it's been a pleasure. See you next time.